Welcome back. In this video, we shall learn about the transportation problems and how they are connected to the linear programming problems. By transportation problem, we mean that it is a problem of finding the optimal cost of the transporting the items from the various sources to various destinations. This problem is usually represented in a matrix form where every cell in the matrix is assigned with the cost of transporting one item from the respective source linked to the cell to respective destination linked to the cell. This problem can be solved to find the optimum cost only if the available resources and the destination requirements are known for all the sources and destinations respectively. For example, consider a simple transportation problem as shown here. The number 80 is the cost of transporting one item from the source S1 to the destination D1. Likewise, 215, 100, 108, 102, 68 are the cost of transporting one item from the respective source to the respective destinations. The numbers 1000, 1500 and 1200 are the total available resources in the sources S1, S2 and S3 respectively. The numbers 2300 and 1400 are the requirements in the destination D1 and D2 respectively. Basically, this problem is a linear programming problem, and hence we shall express this problem as a linear programming problem. The ultimate aim of solving this problem is to transport the item from various sources to the various destinations in such a way that the cost of transporting these items is the least. At the same time, all the items from the sources are utilized and also all the destination requirements are fulfilled. This is possible only if the total number of available resources is the same as the total number of destination requirements. To formulate linear programming problem, let us consider the variables as x11, x12, x21, x22, x31, x32 such that x11 represents the number of items transported from the source S1 to destination D1. x12 represents the number of items transported from the source S1 to D2 and so on. Hence, 80 times x11 plus 215 times x12 plus 100 times x21 plus 108 times x22 plus 102 times x31 and 68 times x32 is the objective function of the transportation problem, which gives the total cost of transportation and hence is to be minimized. So therefore, we can represent the objective function as minimize p is equal to 80 times x11 plus 215 times x12 plus 100 times x21 plus 108 times x22 plus 102 times x31 plus 68 times x32. The restriction for available resources and destination requirements provide the constraints for this problem. Hence, we have the constraints x11 plus x12 is equal to 1000, x21 plus x22 is equal to 1500, x31 plus x32 is equal to 1200. That is, the sum of the allocated resources to the destinations D1 and D2 from the sources S1 is 1000, from the source S2 is 1500 and from the source S3 it is 1200. Also we have the constraints x11 plus x21 plus x31 is equal to 2300, x12 plus x22 plus x32 is equal to 1400. That is, the sum of the resources received by destination D1 from the sources S1, S2 and S3 must be 2300. And that received by destination D2 from these sources must be 1400. Moreover, all these are possible only if 1000 plus 1500 plus 1200 is same as 2300 plus 1400. That is, the sum of the available resources is the same as the sum of the destination requirements. To summarize, the linear programming problem of the given transportation problem is minimize p is equal to 80 times x11 plus 215 times x12 plus 100 times x21 plus 108 times x22 plus 102 times x31 plus 68 times x32 subject to the constraints x11 plus x12 is equal to 1000, x21 plus x22 is equal to 1500, x31 plus x32 is equal to 1200, x11 plus x21 plus x31 is equal to 2300, x12 plus x22 plus x32 is equal to 1400, and all the variables x11, x12, x21, x22, x31, x32 are all greater than or equal to 0. Hence, this transportation problem can be solved by simplex method. Due to the existence of more number of variables, solving in the usual way may increase the complexity. As a result of this, an easy way of computing is devised, which at the background follows the simplex iterations. We shall learn more about it in the next video. Thank you.